Hello everyone. Welcome to this Microseismic Inc. webcast on the future of hydraulic fracturing, getting it right at every stage. My name is Peter Duncan. I'm the founder of MSI, and I'm here to give you a little bit of my vision on what we're going to do with microseismic monitoring in the future. A few weeks ago, I was invited to participate in a panel on the future of hydraulic fracturing at the Tudor, Pickering and Holt Hotter Than Hell conference. It was a great conference with a lot of wonderful speakers talking about different aspects of our industry as it exists today. In our particular panel, the moderator, John Gibson, asked me to be a bit provocative, to step out there, to cause some consternation amongst the audience with what I was suggesting would be the future of hydraulic fracturing. I started off by telling everyone in the audience that at MSI, we have on the walls in our office our motto, which is that a better frac will lead to a better world, and our vision, which is a world in which every frac is monitored because of that motto. What I'd like to talk to you about today is how we're going to get there, how we're going to realize that vision. But before I can talk about the future, I have to talk about the past. Microseismic monitoring of wells, when we got into this business more than 15 years ago, was largely delivering to the client the hypocenters of the events, that is, their position in time and space, what we rather disparagingly call the dots in the box. Why do we disparage that? Because they were of limited value. Oh yes, we could see mechanical failures, bad cementing, casing failure, balls not seating, plugs failing, by watching the dots appear again and again at the same stage when they should have been moving from toe to heel on the well. We could see geologic failures when we'd run into a large fault and the dots would almost immediately start running out of zone, either off to the east or west or up or down, being in danger of hitting into an aquifer and watering out the well, or perhaps inducing some seismic events that could be felt on the surface. We could draw envelopes around these dots and get the gross geometry of where we might think we were draining, but that proved to be pretty wrong any time that we had look back on production. And we could kind of see gross efficiency. Was one well produced better than the other? One stage producing better than the other, or one well treating better than the other by the number of dots. But we soon found that the number of dots did not necessarily all the time correlate to production. Now, the value of these dots, there was value, and it did cause us to grow a business that perhaps penetrated 4% of the market. The value of those dots was enhanced if we could deliver the answers or these dots in real time. If we could tell that the casing had failed or a fault was failing and stealing, becoming a thief zone of our frac early. So we did spend time developing the ability to take the processing system that was needed to process these data, to analyze these data, take it out in the field, and be able to ship our results from a frac anywhere in the world to anywhere else in the world. So we did go to real time a number of years ago, and that did help us move towards our vision. But our clients told us it wasn't good enough. So we were driven to go beyond the hypocenters to start to look at the focal mechanism of each and every one of the events. And that knowledge of the focal mechanism allowed us to replace the hypocenters with fracture planes, each fracture plane representing our idea, our simplistic model perhaps, but our best model of how we thought the rocks broke. Where, when, what strike, what dip, what rake, what sense of motion, and what size of fracture plane was created by each and every dot that we saw. Well, that led us to be able to develop a better image of each one of these treatments. That is, an image that gave us the frac volume and the enhanced permeability volume around the well with very strong physical meaning. And to take that enhanced permeability volume and put it into a reservoir simulator in order to estimate the production and the drainage volume around the well. That had always been what we were told was question number one. How much volume am I going to drain from that one well? And what was interesting about this, getting to this point, is that it wasn't based on some model or some well log and some model around the well that was radially isotropic. No, we were using an in situ lab measurement, if you like, of something that incorporated all of the treatment parameters, good and bad, all of the failures during treatment, the rock properties, the reservoir properties, the in situ stress values, the density of the fluid that you were pumping, the proppant density that you were pumping. Yes, we were in the field observing everything that happened and turning that into an estimate of the production prediction and the drainage volume for that particular well. Interestingly enough, I thought getting some ideas of the EUR from each of these wells would be important, but the engineers were not so keen on that. But what they were extremely interested in is our ideas of how big a volume would be drained by a given well and how that volume changed as they changed the treatment parameters. Now, I then thought, look, we're going to give you a drainage volume and we're going to tell you what your well spacing should be, and then we can monitor every well and you can customize the spacing based on that estimate. No, the engineer said, once I've set up the spacing from that one well, I want that template to be repeatable over and over and over, so I'm going to go drill those wells on that spacing. And based on that initial design, in a way, they were saying they're going to have to pump and pray. They're not going to monitor every well. They're going to put that spacing in based on best data they had to that point, drill every well with that spacing, drill their field out with that spacing, and as I said, pump and pray. Now, of course, we know that the geology in these reservoirs is highly variable. From well to well, in fact, from stage to stage, we see, even with the same parameters of treatment, we see a high degree of variability on how each stage treats. So this pump and pray approach is going to, and in fact does, lead to well hits, to leaving hydrocarbons behind, that is, under stimulated rock, to inefficiencies, pumping longer than you need to, or pumping not as long as you do need to. When you don't monitor, you don't see what really happened, and you can't react to it. So therein comes what is our next idea, the idea for the future of monitoring and hydraulic fracturing. And that is to monitor every well, every stage, and cook it just right. That is, watch that stage based on your template of spacing about how much each well has to drain, and watch it as the frac goes forward in real time. And you may plan for 2 hours, but if you haven't stimulated the rock correctly in 2 hours, then we're going to tell you, keep cooking. You may plan for 2 hours, and if you've reached that area of coverage for that stage within an hour, we're going to tell you to stop. And you can save that hour's worth of cost for that pumping. In other words, cook every stage just right by monitoring every well and every stage. Now you're going to say to me, Peter, I can't afford to do that. Monitoring a well costs $100,000 to $300,000. I can't afford to do that on every stage. Is there an answer to that? Yes. That answer is a buried array, a permanent life of field monitoring facility. And frankly, we've already put these in all over the country and all over the world, in Argentina, in England, in Canada, and all over North America. When operators have realized the need to monitor a large fraction of their wells, a downhole monitoring sonde next to each well just doesn't cut it. It's too expensive. A temporary array on the surface consisting of thousands of channels for a pad or across a field is just too expensive. It doesn't cut it. But if we put in a buried array, cement the phones in below the surface, 4 to 8 phones per square mile, and then occupy those phones every time you do another well, we can in fact drive the cost down. We've been doing this, driving the costs down to less than a few $1,000s per stage. That makes it attractive, and it makes it economically feasible to monitor every well. In the old days, I used to have an image that I would convey to people, sort of my elevator pitch. What is microseismic monitoring? And I'd say to them, it is a stethoscope put on the chest of the reservoir to listen to the squishy sounds that are made when you interact with it when you frack, in order to tell you how well you're doing. The problem with that image is that it was a seismic image. It was the gathering of data. It may have been data and it may have provided certain knowledge, but it didn't allow for action. So now we're changing our model to accommodate this vision of monitoring every well and cooking it just right. Yes, folks, and I hope you're smiling, but we are now realizing that what microseismic monitoring is, what MSI really provides, is a meat thermometer in your reservoir, allowing you to judge when you've fracked, when you've cooked every stage just right. At least that's the way I see it.